Hello, everyone. Welcome to this last lecture of the semester. We will continue with things that don't fit nicely in the TCP-IP architecture. And the first topic today is Mpls. Mpls is something that is widely used in operator networks, Swisscom, Orange, etc. They all use Mpls, but it's not visible to us because when we ping, when we trace route, we don't see it. So what is it? It's called multi-protocol label switching. And as the name gives, the idea is to be able to carry over a wide area infrastructure, multiple protocols in the sense of other than IP. So as I said, it's widely used in IP backbones of internet service providers. It's also used, for example, at interconnection points. We've mentioned May West, May East, so those are places where multiple operators peer for BGP. Then we typically use MPLS in those points to interconnect those. And we will see one very funny application, which is extremely important today, is to interconnect private IPv4 address spaces. In spite of the development of IPv6, there is still a majority of addresses that are in fact private IPv4 addresses, because you can have as many as you want. Any company can have them. EPFL has them in the backbone of EPFL. When you connect to the VPN, for example, you have 10.something addresses. So EPFL, like many companies, uses those private addresses. And now if you're a carrier, Switch, Swisscom, Orange, you need to interconnect all those private domains. And you cannot do it by simply doing the standard IP that we've said, because those private IP addresses are private. So one way to do that is to use MPLS. MPLS is based on another principle of the connection layer, which is sometimes or often called the connection-oriented network layer, as opposed to connectionless. So the IP network layer that we know, IPv4, IPv6, apart from format details, they are exactly the same. And IPv4 and IPv6 are connectionless. So what's the difference between connection-oriented and connectionless? Well, connection-oriented is in fact the first packet switch network, the CICLAD network that was developed in France, was using exactly this principle that is shown here. So we send packets, but we establish connections through the intermediate systems. The intermediate systems were called switches in the old days. Now they continue to be called routers, because as we will see, MPLS routers, they run both MPLS and IP side by side. They run both MPLS and IPv4 and IPv6, in fact. So we are used to that. We know that routers can run two routing protocols. In fact, here they run three. The third one being MPLS. But MPLS is radically different from IP. We send packets. Packets have, they don't have a destination address. They have a label. A label is a number. With MPLS is on 20 bits. So it's a relatively small number. The space of labels is much smaller than the space of IP addresses, which should be able to address the entire world. Here, a label is to identify a connection local to a link or local to a node. Here, I'm showing, for example, label 2 here. In this connection-oriented system, a label is identifying multiple connections on the same physical link. So here on the link between A and S1, there are two labels, 2 and 1. And the rules are that the switches on the way, when they see a packet with label 2 here, that come here, they will look at the label, go to a table, which is the forwarding table, except now it's in the forwarding table, we do exact match for labels. So here we see that the input number 3 and value of label number 2, which is given here, this third column, this second column, corresponds to an output and a new value of the label. Here the value is the same, but the value could be changed. So the switching function is entirely based on the labels and is local to this switch. The switch here doesn't know whether this packet is going to C or to B. It simply knows what to do because it has a table that does it. So if we follow this connection, this green flow or connection, we see that at S2, it will go to output number 3 with label 1, and at S4, it will go to number 2. In contrast, the red label here, the red flow, at S2 will go to a different output port. So said like this, it's extremely simple. The labels are present, for example, in virtual LAN IDs. If we use virtual LANs, that's an example where you could do exactly this, and then the green flow would simply correspond to a virtual LAN ID. So that's the idea. That's in MPLS, that's very close to that. Of course, there is a price to pay for that. There's a hidden complexity. Which one? Well, you need to set up those flows before. So in order for A to be able to send one packet to C, we must first make sure that all the switches, that we find a path, and that all the switches here decide on values of labels and write the exact correspondences in the table. We say that we need to set up the connection. In fact, this is what was done up to 3-4 years ago when the telephone network still existed. Telephone networks were built exactly according to this, except for telephone networks. Those were physical connections here. If OR A calls C, you had the switches that were set so that the green flow goes here or there, depending on how you called here. So how did you set up the flows in the telephone network? Well, you dialed a number, and this number created a machinery, called the machinery, that would set up the flows here everywhere. So here it's the same. Before this to happen, we must set up the labels. How do we do that? We can do that with SDN. We have seen SDN can always be used to do anything centrally. So we can have a centralized network management or network control application that will do that. There are also what is called signaling protocols that are able to do this. A signaling protocol, the terminology means a protocol that is used to set up the label associations. The terminology comes from the telephone network. In telephone, we do signaling. When I call someone else somewhere else, the numbers are used to set up the path. How do we do that in today's MPLS systems? Well, all those boxes, they run not just this, but also IP. So for example, if you run OSPF, you have a view of the entire network with OSPF that allows you to compute a path. And once you've computed the path, you can send messages to all the systems on the path on the way to agree on the labels. There are different protocols for that I will later mention. Some terminology. So first, the label swapping table or label switching table, also called the forwarding table. In modern routers, in fact, it's mixed together in the same big table as used for IP routing. But the difference here is that we need to do an exact lookup. So it will not scale to millions of addresses. It's not made for connecting a small end system to a small end system. We will see that, in fact, it's made for connecting edge routers to edge routers here. The end-to-end connection is called a label switch path. In terms of header, if we do a Wireshark, we will see that from the Ethernet header. So the MPLS label is carried immediately after the Ethernet header. And if there is an IP packet, it is carried inside the MPLS packet. Although the MPLS header is very minimal, it contains primarily the label, some information for quality of service. Quality of service is the same quality of service we've seen in IP. This is used, for example, if you want in a provider network to make a difference between labels or label switch paths that are used for interactive video and audio versus batch transfers. Or different customers may have different, they paid for different tariffs. We know that Swisscom, for example, gives you different cellular telephony access with very small to very large at different prices. Here, one way that they can map the quality of service that they provide to you in their backbone network is by mapping the different flows of different classes of customers into different type of service. And then using things like we have discussed when we talked about schedulers inside the network, we can guarantee different bandwidth to different LSPs, label switch path. There is also a TTL, which is the same as the IPv4 TTL, and a bit here that is used to identify whether this is the last label, because labels can be stacked. They can be a label, and inside the label, there can be another label. We will see a use of that in a second here. So in order to know whether this is the last label, there is this bit that indicates this. So if you're a router and you receive such a packet, hopefully you are running MPLS, because this, if you look at the protocol type seen from Ethernet will indicate that's MPLS. So since it's MPLS, you will analyze the label, look into your label swapping table, and act based on this. That's the normal case. In special cases, when you're an edge router, as we will see in a second, this MPLS connection terminates at you. If it terminates at this router where you are, then you need to continue. You look for what comes next, and the next thing might be an MPLS header or an IP packet, depending on how many labels there are here. Let us see a typical example. So I skipped texts of the slides, but the text is exactly the explanatory text I will give here. This is a backbone network that has 6 routers. The routers are running IP, like any router does, IPv4 and IPv6 probably, but they also run MPLS. So all those 6 routers run MPLS. And in the world of MPLS, we do a distinction between what is called edge router and non-edge router. So LSR stands for label switching router. It means an MPLS router. And an LSR that is interfacing between non-MPLS world and MPLS is called a label edge router. In the example that I am showing here, this is used for interconnecting private IPv4 addresses. So here I have 3 customers that each have their own VPN or their private address space. For example, you could imagine this is EPFL, and this is different campuses of EPFL that are interconnected by this operator. So we have a green, a blue, and a red private network on the left and also on the right, and the same color corresponds to the same organization. So the green addresses correspond to the same customer. The service that is provided by this ISP is the interconnection of this private network, and it should be entirely private. There should be no way to leak information from green to blue. For example, a green packet should never be forwarded to a blue interface, and vice versa. And in fact, you see even here that the green and the blue are reusing the same address space. They're both using the 10.10/8 prefix here. In order for this to work, the provider will set up an LSP to interconnect the green sites, for example, the green LSP, and the decision of the provider is to follow this path here. So we will see here how the tables are set up accordingly. At this LSR-M, the first one on the path, there will be a label that says whatever comes on label 50 should go out with label 34 on output port A. Here I'm showing an example where the labels are global, local to a node. Local to a node, that means when LSR receives a packet with label 50, it knows what to do with the label, regardless of the link that the label arrives on. The 2 variants exist in MPLS, so you have to MPLS is very complicated. Has lots of variants, although the principle is very simple. Here I'm using, this is the most widespread variant today. In the previous slide that I showed, the same label could be used on different physical links. Here it cannot. That's a small detail, but that explains why here I don't need to give the input port on which the packet arrives, because the scope of 50 is to all links of this router here. Of course, the label swapping table must be set up consistently. Here on the next router, we will see that anything that comes with label 34 is switched out on port A with label 49, and it reaches router B here with a label 49. So one thing that we observe is that the label has no global meaning. It's local to a node, but we see that, for example, seen from A, the label switch path that is used to interconnect the rest of the green virtual private network, is label 50, whereas for B, it is label 49. So the value here must be set up when we set up the switching path here. When we set up the path here, this value is chosen based on the values that are available. Perhaps, for example, this path was set up before and the 50 is already taken, so we could not reuse 50 here. But B, of course, knows what are the possible labels. So similarly, we see that the blue VPN uses another path. Why does the blue VPN use another path? By default, this would not happen. If you let MPLS run with all the default values, MPLS will always compute the shortest path. In fact, one very simple way to set up the labels is to use the routing of IP. For example, here I have the job of setting up a label switch path to router B. How can I do that? Well, I will ask my routing table, which way should I go, my IPv4 routing table, in order to go to B. And if the next hop is M, the label switching protocol, called LDP, Label Distribution Protocol, will simply follow what the IP routing table says. So it will go here and it will ask M, hey, I would like now to continue setting up the label. I have picked label 50. Please pick one label, which is not 50 because 50 is already used. And here it was chosen 34 and etc. If we do that, of course, the blue and the green label will follow the same path. That's the default behavior. Very often providers may want to do different things. For example, if they choose different quality of service requirement, perhaps the green and the blue are in different traffic classes, the X small or the XL of a Swisscom, for example, then they might choose different paths. Perhaps this path here, there is a bottleneck there that is shared, that we don't want a lot of traffic to go there. So therefore, the blue might avoid the bottleneck to have better quality, for example, or vice versa. Also, there are other protocols than LDP. One of them is called Rsvp, Resource Reservation Protocol, that will try to find a path while specifying a required bitrate. So we can set up a path by saying, not just how do I go there, but I may set up a path with, for example, a guaranteed rate of 10 megabits per second. Remember, we saw that there are schedulers and routers, like deficit round robin, that are able to provide such guarantees. So one of the what is called traffic engineering uses of MPLS is to do that exactly. Based on the business contract we have with a blue and green customer, we may guarantee, for example, to the green customer that its backbone service will receive at least 10 megabits per second, and for the blue, perhaps at least 30 megabits per second. Then we will set up this path while computing the bandwidth that is reserved at every hop. And this is very easy to do. For example, if you have OSPF in your network, you know the entire map, you know all the links, then you can add to OSPF. There is an extension to OSPF that will do this. You can add to OSPF the information of how much bandwidth is already reserved for the LSPs that are already set up. So that might explain why the paths are different here. If we do a Wireshark here at this link here, we would see, for example, a packet, a blue packet that will have an Ethernet header. This link is the Ethernet, a label 49, that's the outer label. And then another label, label 78, is in fact a label that means the blue customer, the blue virtual private network. Because if you remember the MPLS header, the MPLS header has no protocol type. In principle, every protocol should have a protocol type to indicate what is the next protocol that's carried inside it. Ethernet has a protocol type called ethertype that says this is MPLS. If instead of the ethertype it would be IP, it's Ethernet that says it's IPv4. And then IPv4 will say inside the IP header, this is a UDP or a TCP packet or an ICMP packet. MPLS doesn't have that, which is weird perhaps, but perhaps the reason is also to save space, to make the label small, although it doesn't really save space because the trick that is found instead is to use another MPLS header that will identify two things. First, the protocol type and the type of customer. So here, if I go back to my example, oops, sorry, wrong direction. Here, we associate the label 78 to the blue customer, to the blue VPN. That means that router A and router B here, they associate this label with the blue customer here. And this label is not changed by the intermediate routers because their job, as long as they have a label to switch, here label 49, when you find in the table an action that says the output is A with a certain value, then you don't touch the rest. You just look, you're just happy with what you've done here. In contrast, if we zoom here at what happens at the edge routers, here this is A, so this is a part of the forwarding table of A, and here this is a part, I say a part because I'm showing only a fraction of the content, the one that I discussed. We will see, for example, that if I am at B, when I receive a packet that has a label 49, that's the packet that's on the green floor here, it says pop. Pop means remove. Remove the label. That means I am the end of this MPLS connection. So I will remove the label, and after removing the label, I still need to do something. Now I have a packet where I've removed one label, so I look at what is the next header. And the next header is again an MPLS label, because this packet contained here, if you remember, if you look here, the packet, this is the packet we're talking of. Once you remove label 49, presumably you will find label 24. So you go to one of the rules here. You could have multiple internal labels. Here I'm showing only one. And you go to the next rule that has an exact match. The next rule that will have an exact match, because you've removed this outer label, is label 24. And now the label 24 identifies the green VPN. Now we will find something that is very interesting, and that's all the power of MPLS. MPLS is not just doing label switch path using the connection-oriented principle of the connection layer. It's also doing the bridging between the two worlds, IP and MPLS. And here, this is where the bridging happening. When I see a label 24, I remove it, and I go to my routing table, but not to any routing table. I go to the routing table with the additional information that I am in the green VPN. Green VPN here means VRF, virtual routing function. So virtual routing function simply means that inside a routing table, you may have multiple private address spaces, which is exactly what happens for this router. This router on the right here, this is a non-MPLS set of links. So this is normal IP interfaces. Except you see there are some interfaces are on this green domain and some others are on the blue domain here. So the router should know that interface F belongs to a virtual IP world, which is the green one, which is not the same as interface D, which belongs to the blue one. That should sound familiar. We have seen the same trick for virtual LANs. With virtual LANs, we did that at the MAC layer. Exactly, we can configure a LAN switch to say this port belongs to the red LAN, this port belongs to the blue LAN, and when I look at the MAC addresses and I do a spanning tree, I will do completely separate things for each of the colors. Here it's exactly the same thing at the IP layer. At the IP layer, we do also virtual IP worlds. They are called virtual routing functions, and they are done quasi-systematically everywhere in the internet, which means I have, in fact, multiple routing tables inside my routing table. Of course, I need to know in which routing table I am. I know that because from MPLS, through the label here, the label says that's VRF1. And then, for example, if I have a packet with destination 10.2.2. something, then the table says, if I am in VRF equal to 1, I go to output port F with next hop, whatever. This is the standard IP routing. And of course, similar things will exist. So the routing table of B will be very large. It will have a private routing table for the red, for the blue, and for the green. If you look, for example, at what happens at the last table here, this is what router B should do when it receives an IP packet that belongs to VRF1. That means to the green VPN. How does it know it belongs to the VRF1? Either because it comes from MPLS, or because you have configured the interfaces of this router with a VRF value here. So this is done statically, so you cannot mix in such a router. If you want to mix multiple VPNs, you have to use MPLS. If you on the same interface, we can mix here on the link between N and B. I can have traffic of two VPNs that is carried, the green and the blue. It's possible because I use MPLS. Here on the interface F, I cannot. Interface F must be dedicated to the green VPN. So in the configuration, if we do the if config of this router, we will see VRF equal 1 to the interface F. And if we look at what happens when I have a packet that comes that has destination address 10.1.16/16, that means a packet that should go here to the other side of this provider network. What will the router do? Well, the table says, well, for this destination, push label 24, which means I will send it with MPLS here, and push label 99. That means I will push the label 24, which identifies the green VPN, and the label 99, which is presumably the reverse path that is chosen for the green VPN from B to A. LSPs, in principle, label switch paths, are one way. They go in one direction, but of course, typically, communication is quasi always two ways. So you must also have a reverse path, and we see here that it is done with this label 99. So this is how MPLS, if you contemplate this example, I am an ISP. I can interconnect my private domains here. And believe it or not, today there are more end systems that have private addresses than public addresses. In fact, in the world, we know that from home because we use a NAT at home. So this is how we can do that and interconnecting everything while preserving the IP addresses here. Here we have done no NATing. The 10.1 can communicate with the 10.2, but cannot communicate with the 10.2 of the blue, for example. In order to do that, we will need to go through a NAT because we're reusing the same addresses here. So this is only for private communication inside the domain, which is a large fraction of the internet traffic because all the business traffic is using this setting. In fact, we have already encountered MPLS a few weeks ago when we spoke about BGP. The problem we had in the previous slide was how do I carry the traffic from A to B over my IP infrastructure, but I don't want to use IP forwarding because my routing tables are not able to, if I would not use MPLS, what I would need here is to do a virtual forwarding routing function everywhere in all the backbone, which would be making the backbone very complicated. We had exactly the same problem with BGP. Remember that when we have a domain here, that's for example a tier 3, so somebody that's some domain that's at the core of the internet, that is it has to carry all the destination addresses, so 1 million IPv4 prefixes. So we know that these edge routers that run BGP will know about or learn about all these prefixes. But in order to be able to carry packets inside the backbone, I also need to distribute all those prefixes into the backbone. And we've seen there are two methods to do it: redistribute OSPF into BGP, or the interior gateway protocol into BGP. Very often, this is done sometimes, but not always, because at the end of the day, we put all the complexity of BGP into OSPF. So another thing that is done is to simply run side by side BGP everywhere, which is done by some providers, but some other providers prefer to use MPLS instead. Because if you think about it, the problem, as long as you don't want to this router to talk to web servers that are somewhere in the rest of the world, which is typically not what you want to do. In fact, you want to hide your infrastructure from the rest of the world. You want it to be private so that nobody can attack it. So those routers, typically, they are not expected to receive packets that should go to 18.1, for example. They talk only to the network management of this company here. So we have, again, the same problem. We need to carry lots of IP packets from R2 to R6, for example, to 18.1. But we don't want to bother R1 with the information on how to go with the 1 million possible prefixes in the world. And then it's completely obvious that MPLS is a good solution for that, because BGP, what BGP says to what information is available through BGP is the next hop. So BGP knows for every prefix, like 18.1 in R2, we know for 18.1 what is the next hop that we should send. So what BGP gives to every router is an information of the kind. In order to go to this remote address, go to this next hop, which is in your domain. This is what BGP does at the end of the day. All the complexity can be summarized into that. So this router R2 now has to send packets for transit packets to all the BGP border routers. And an obvious way to do it is then to set up an LSP to all the BGP border routers. So all eBGP routers in this transit domain will set up label switch paths to all next hops, in fact, of all BGP routers in the same domain. So for every next hop address, I will set up a BGP path. And when a packet comes here, this first eBGP router that will see the packet will find in its routing table the next hop. For example, at R2, we will see 18.1/16, next hop is 2222. We've seen this is what BGP does. It injects into the forwarding table the next hop. And this next hop is not on link, so we need a recursive table lookup. The router sees 222 is not on link, so I need to go again into the routing table. And now we will have an MPLS instruction. In order to go there, push some label, which is the value of the label, that leads to 2222. And we'll go on this interface. So at R1, similarly, when I receive label 23, I need to go to label 123. And this has been set up because LR2 maintains LSPs to all possible next hops here. So we see that the router R1 completely ignores the complexity of the internet. It sees only, it has a complexity, which is the mesh of all eBGP next hops to all eBGP next hops, which is considerably smaller. If you have a domain that has 200 points of interconnection, that means that there are order of 200 square such possible connections, and all of them will not go via a single router. When the packet comes at R6 here, then there will be, it's not shown here, but at R6 we will see that there will be an instruction that says when I receive the label 123, for example, then I should remove, so pop the label, and then I will look for the next field that will be indicated, go to the IPv4 routing table, if this is IPv4, and therefore the IPv4 routing table will have an entry to 222. That will be given here. So this is solving the problem of interaction of BGP and MPLS. And incidentally, it's also multi-protocol. Here, I can have, it will work for IPv4 as well as IPv6 here, but we will typically need different label switch paths for IPv4 and for IPv6. In what I've shown, I've assumed a lot of manual configuration. In particular, so for setting up the label switch path, I've mentioned the protocol LDP that can do it automatically using IP routing, but there remains manual configuration, which is explained here. How does this know that it has to set up a green label for this site here? Of course, if you're an ISP and you have only 3 customers, that's easy to do. But of course, if you're a big ISP like Swisscom or Orange in France, you will have, at least for Orange in France, probably hundreds of thousands of customers. So you need to automate this. And the funny thing is that this automation, well, not the funny, but the logical thing is to use BGP. So assume you're a customer here, like the green customer, you connect it to your provider at 2 sites, this one and that one. So that's EPFL Vallis and EPFL Lausanne, and this is, for example, switch here. And assume you want to still have connectivity for your private backbone, which is invariably the case. because companies are lazy and they want to use IPv4 addresses. And if you want to use many IPv4 addresses, you have to use the private addresses. That's one reason. The other reason is that companies are serious about security, and having private addresses make it much more difficult to attack. Right? In fact, MPLS is invisible to us from the outside. We cannot inject an MPLS packet into Swisscom. The only way to inject it is to take the control of this label edge router here, which is inside the Swisscom domain. So you need to hack a Swisscom central office somewhere, get access to the physical router, or hack one of the servers or one of the network management consoles that can get into those routers. From the outside, what we have is no MPLS. We have a standard IP interconnection from, for example, the router G1 or the routers G2 and G3 that correspond to different, here we have two sites, but even in the second site, I have multiple subsites. I have subnets that are physically connected to different connection points of the ISP. So the normal protocol to carry my information is BGP. Carry my information here means I would like that automatically two things happen. First, the green customer automatically discovers that there are two other green customer prefixes that are here, and that they should be the level edge router should do the right thing automatically in its. We've seen it uses virtual routing function in its routing table. So that's the first thing we should do. The green customer should be able to do that automatically. And the second thing is that the provider should be able to discover there is a green customer and I need to do something about it, as well as a blue and a red here. So the way this is done is by BGP. So you're in the middle or at the end of your BGP lab. So we know how to configure BGP routers. So here, the green customer will advertise all the prefixes that it wants to prefix to the provider. That's the only network, presumably here, that it's connected to. So it will send an eBGP update. And the eBGP update says, when it's received by A, it says which is the next hop. So next hop is something on this link here. And a private an AS number, which is probably a private AS number because this is a private network. So it's of interest only to this ISP. So if this ISP accepts this announcement, if it corresponds to the business relation that was signed between the two, and if it's the best path, it will accept it. So it will put it in its RIB chosen as best path, and it will have information of the type. The prefix 10.1/16 corresponds to next hop, which is this one here. And of course, we need to configure now some information that says this is the green customer. So there is an attribute in BGP, it's called route distinguisher, that says this is the green customer. Route distinguisher means it is an attribute that makes this a separate route, a separate set of addresses, which is the case for IP addresses. So two routes that have different route distinguishers are distinct routes, and they belong to different worlds. So here, the route distinguisher green, of course, you need to configure your BGP router here to say everything that comes, for example, from ASGA corresponds to route distinguisher green. So we have this additional attribute. And of course, there will be a similar 10.16, then 10.116 received from B1, but it will have a different route distinguisher. So it will be a different route. It will never be compared to that one. Then when it receives that, it will inject it into its forwarding table. And you need also to configure BGP to map route distinguisher green to what is called the virtual routing function that corresponds to green. Here it's a bit ugly. The route distinguisher and the virtual routing function exist separately, so you need to map them. So this will be put into the routing table here, and we know at least how to go to 10.1 in A. Then A will send an iBGP update to B, because B is also a BGP router. Here. And through the BGP mesh, A will send, here is the best route I have to this destination. This destination, here is the combination of the IP prefix and the route distinguisher. B will accept it, presumably. So B will accept this and put it in its RIB here. It knows now there is a 10.116 with next hop 10.1.1.1 and route distinguisher green. And then B, depending on how it's configured, it's presumably configured to do Mpls and not the other methods we've done, will therefore put into its forwarding table the consequences of that. The consequence is, how do I go to 10.1? Then from our routing table, I see that 10.1 is not on link with me. And in such a case, I will establish a label switch path, and I will put into the forwarding table the corresponding label. And also the corresponding label that corresponds to green, the entry that we saw a few minutes ago, which is this one here. This entry here will be put into the forwarding table as a consequence of receiving and accepting this BGP update. Then if this BGP update is accepted, then it should speak with to the green customer via eBGP. Of course, a route distinguisher green means that only such routes can be exported only on interfaces that are labeled to be authorized with a route distinguisher green, which is how those two green interfaces here. So G2 and G3 will receive a BGP announcement that says for 10.1.16, what is the next hop? Well, the next hop will be the interface here. The AS number typically will be the AS number of this provider, because this was a private AS number and we don't forward it. Therefore, the green customer will accept it and will be able to inject into its routing table and perhaps also redistribute into OSPF, because here the number of prefixes we have is not huge. So this is a case where redistribution is typically done. Therefore, G2 and G3 will learn that 10.1 exists and has to be sent to B instead of being routed in different ways internally. So we see that this mechanism allows to do things that otherwise would be completely impossible. It allows to distribute the routing information, which is entirely private, inside the private domain by running BGP across a public domain, across the ISP. This is the typical combination, which is called multi-protocol BGP, MPBGP for Mpls. And this is how very much a large fraction of the internet today works. Label stacks. Label can be added on top of each other for identifying the VPN that's at the other end. But Mpls is infinitely complex. You can do zillions of things. It's almost like a programming language. It is also used to do things like this one for scalability. The principle of the connection-oriented network layer is not scalable. You need to set up a path between any end system and any end system. So you cannot do that for running the web, for example. My PC cannot establish a path to another PC in the world, because if I do that, the intermediate systems will have millions and millions and perhaps billions of paths to manage. So we have square N. It's even worse than IP routing. However, as we've seen, it's used for interconnecting edge routers, which are much smaller number than the number of hosts, but they can still be many. So a way to address scalability is always the same. It's called divide and conquer. If you have a non-scalable scheme, then you make it scalable by grouping things together. We've seen that for the iBGP mesh. The iBGP mesh is non-scalable. So we use confederations or clusters to to solve the scalability problem. Here it's the same idea. If you have a number of edge routers that go via the same direction, via the same path to a number of other array edge routers, you can group all those MPLS connections, all those LSPs into another LSPs. So here it's a non-edge router. It's a backbone router that will decide to multiplex here 3 connections into 1 here. Of course, the 3 connections that are multiplexed into 1 now are sharing the same quality of service, but that reduces the number of connections that are visible in the backbone. So if we do Wireshark on this link here, we would see, for example, that we have a MAC header followed by a first LSP, a first label 50 for this here, followed by label 10, which is, for example, the value that corresponds to one of this, but may have been changed here, followed by a label 89 that identifies the VPN. So we can have up to 3. That happens a lot. That is how we can make things more scalable. So this I'll explain. Now let's conclude this MPLS story with a little wake-up quiz. Oops. So in this quiz, I'm asking, how does router D, so D is, where's router D? There is no D, so no. It's here, okay, thank you very much. So how router D here knows that the packet to be forwarded to C2, this one here, is an IPv4 packet here. And this is how the packet would be here. This is if we do a Wireshark of the packet before it reaches B, this is how we'll see that. I'll close in a few seconds. Closing. There's a tie for B and C, but the correct answer is C, because, well, if you look at the header, which is here, once you've removed the header, you don't know which packet you have. Of course, you could do a deep packet inspection and see whether by matching the bits, you find exactly the version, something that looks like an IP header, but that's very risky. I mean, this is just a string of bits, the packet here. We interpret those bits as this is a header, here is a destination IP address, but because we know it's an IPv4 packet, we expect the IPv address to be at this location. If it would be a MAC layer packet, for example, or an IPv6 or an AppleTalk or whatever weird thing, it might very well look like an IP packet. So it's not possible by either this. The ether type indicated it was MPLS, and the version number is a version number only if you know that it is an IP packet. So no, that's not the way it's done. The way it's done is that this inner label here, the label 89, identifies that it is, identifies two things, identifies that it belongs to the red customer, so we should use the virtual routing function that is red, but also that it is IPv4. It is a virtual routing function for IPv4. So if we would have IPv6 and IPv4 private domains here, we would need to set up two separate labels here. That's the conclusion about MPLS. That's all we'll do for MPLS. Before releasing you for the break, we'll do another thing, which is the due feedback on evaluation. By the way, I was asked to incentivize you to give other feedback on the new evaluation, because we have two evaluations. So, we love that a lot. This is the summarized evaluation, which is positive. So thank you very much for your support here. Still, there's a number of, well, the very positive things is first, the assistant étudiant and the teaching assistants were largely very responsive. And so thank you, Stefan, and thank you all the team for giving good support. This year, we've introduced automated grading lab for all labs. We did it last year for lab 3. That was the first phase. This year, we did it for all labs. And first, the feedback is positive. So if I understand well, our intention was to make it more attractive for students, because you can get more immediate feedback instead of before that writing a PDF and receiving a feedback 3 weeks later. This is less interesting. So the feedback that is automated is good, but also not always good, because we had to use Moodle and we had to automate everything. It was a huge amount of work to be done in the previous semester, in fact, by all the team of assistants étudiants and TAs who worked even before the semester. And some of the things we could fix on the fly. It turns out that we could not fix all of them, but for next year we will try to fix all of them. Of course, it will never be perfect, but we hope it will be improved. There are some limitations on fixing that we have discovered a bit late, unfortunately. Once a quiz has been taken by one of you, we cannot add or remove a question. So, and some of you were very, took all the quizzes from the beginning of the course immediately. So we should have closed the quiz, make the quizzes invisible until we're absolutely sure about all details. And if we discover a bug while the quiz is, while the lab is happening, we can modify the question, but we cannot split the question into two or delete a question or add another. That's a limitation of Moodle. So we'll try to debug it so that the problems do not occur. About quizzes, there were also synchronization problems between the lecture and the lecture quiz, which you can see this week, for example. In the quiz of last week, there are a few questions on the tunnels that we will do next hour. This has happened repeatedly due to some synchronization problem between me and me, in fact. And also I thought some of the quizzes were closed or were hidden, but they were not. So sorry for that. We'll try to fix that next year. The lab workload, some complain that it's a bit too much, although we streamlined it considerably compared to the previous years. The good news, perhaps, is that next year this course will move to 8 credits without any change in the number of contact hours. So that would perhaps reflect more truly the workload, and knowing that it's 8 credits, you can perhaps be more relaxed at spending more time on that. Next year, we don't know. We have a problem with the virtual machine. We were confronted with the fact that the Apple machines the newest Macs don't support the same software at all when we do low-level stuff like we do than the Intel machines. So before last year, we were in a happy window of time where all machines, Linux, Windows, Macintosh, were all using the same processor. So we could do a virtual machine that was the same for everyone. This is no longer possible. We will see what happens for next year. So the solution we found was to give Minix to those of you that have, so to have Intel processors. For those of you who don't have it, we'll see what to do next year. Voila, that's for the feedback. If there are any additional suggestions or hints you may want to, or any things you want to say. No, then, well, thank you. Then we do a break, a bit shorter break today, and we resume at 1:15, and we'll finish the rest of this tunnel and other deviations. We have seen MPLS, which is a kind of tunnel in the sense that we carry an IP packet inside something that we can call an MPLS packet. But we can do even worse, and we've done that in the lab. For example, if you use Teredo, a tunnel is, for example, when you carry an IP packet in a UDP packet, or an IP packet in an IPv4 packet in IPv6, or any combination. It's also called encapsulation. The two words are synonym, which of course is something weird that we should not do in principle, but that we do for security or private network. So let's talk again about private networks. The private networks we saw in the first hour were actively supported by the operator. It's the operator that did for us this label edge router that interfaces the IP world and the etc. So we can do it in this way with support from the operator, or we can do it in a way that is completely transparent to the operator. For example, if you run a small business and you have 2 sites and in 2 apartments, and you have an access to Swisscom, for example, and you want to make a true network out of that. You want to interconnect all your machines on the left and all the machines on the right. Of course, one way to do it is to use NATs and public addresses, but assume and make your machines here public, but assume you don't want to do that. You want really this to be a private network. So a classical solution is to use what is called virtual private tunnels, virtual private network tunnel, VPN tunnels. For example, here, the simplest of all approaches would be to configure, so you take a router here and using IP routes and things that we've done in some of the labs, configure here a virtual interface in A that is associated with the IP address of B here. Here it's a simple case because we have only 2 routers here. And then this virtual interface would be encapsulated in IPv4, which means every packet that we put in this interface is put into an IP packet that has destination address 22222. And then it comes in B. In B, you've done the same thing. And it comes as if you had a physical interface. So at A and B, you have 2 interfaces. You have that go to the red part. You have the physical interface that go to the Swisscom network here. And you have a logical interface that adds these encapsulations here. So packets from S to X and vice versa are carried inside IP packets. So for the operator, there's no VPN, there's no VPN service. You just see IP packets carried from A to B. You don't know what is happening here. So assume, for example, we do a Wireshark at this point here. What would be the IP destination address and the protocol that we see at this point here? Little quiz. I close the poll in a few seconds. And the majority of your answers says it would be A, but if we do verbatim what I said, this is not what would happen. So the correct answer in this case would be, in fact, which page number am I? I'm putting my IP packets into IP packets. So if I analyze the header, I will see, of course, an IP packet. But the protocol is not UDP. It is IP, IPv4. So there is a protocol number for IP itself inside IP, for IPv6 and for IPv4. So you can carry an IPv6 packet as the payload of an IPv4 packet, or an IPv4 packet as the payload, or all combinations are possible. So this is what we would see here. In practice, this is very often not done. That exists. This is one of the many options of VPNs. So when you connect to the EPFL VPN using the VPN application, which you have to do for some of the services these days because many of the servers are restricted to VPN, you probably use something else where this is not done because many routers they are configured to avoid attacks or to try to avoid attacks, and they look at weird values into protocol types. And one of the weird values is this one. So many routers will kill packets that don't have a protocol type that is not TCP, UDP, or ICMP. So if you have a router of this kind on the path here, such packets would be killed. So which leads to the stupid but working solution, which consists in putting the IP packets inside UDP. Instead of putting them inside IP, we put them inside UDP. So this is typically what we would do. And then the problem is, which would lead to exactly this. So we would see a UDP packet here at point 2.2. We would see a header that says it's going to, so a packet from S to X would go to destination address 111, a UDP header with a UDP port number, which is not very helpful. The UDP port number is simply the port number used by the VPN server at A to receive all those packets. And then typically there is also another small header, which is just serving the purpose of identifying a protocol. Such a header is called the L2TP header, which is a header that exists, a format for headers that exists that is used to carry all the possible protocols in the world that exist. In practice, we also add, so if you use this technology to connect to the EPFL VPN from home, for example, you will also encrypt the packets. So you will have all those headers, plus what is called encryption and authentication headers, which belong to what is called the family IPsec. IP stands for IP layer security. So there's a set of protocols that says how you, protocols means header and trailer formats, that say how you encrypt and authenticate a packet. Of course, to do that, you must have a shared secret between A and B. And as we have seen, there are techniques to have shared secrets using certificates, which you must set up very much like we did in the labs with TLS. So you set up those secrets between A and B, and then, or very much like for TLS, if this is EPFL and this is you at home, you will use the certificates that come with your VPN software to find these encryption keys here. So this is one of the very familiar versions of VPNs. Those are the ones we use when we have a host access to a network, which is a different configuration than what we spoke about an hour ago, where an hour ago we wanted an entire private network to communicate with an entire private network. Typically, in such networks, there is no encryption because we trust the label edge routers. Everything is encrypted up to the label edge routers. After that, it is or it is not, but it is not encrypted at the IP layer. It is typically encrypted by what is called WANSEC, Wide Area Network Security Layer. We encrypt the physical layer on the links here. So this is the most frequent types of tunnels. I'll skip this. This is the most frequent type of tunnels that we use every day here. And if we do a Wireshark of the thing here, in fact, we will not see much of the packet. We will simply see, oh, that's a VPN packet. Then the VPN packet will contain inside it a packet which has an IP destination address. So the true packet that will be delivered here is encrypted and in fact is invisible, which is also a good security. It's a good protection. If you use the VPN, you make sure that all the traffic that you use is encrypted. So for example, if you're accessing not from home, but from a hotspot, public hotspot, then all the traffic you're sending is invisible, except the fact that you're sending it to this VPN server. That's our first example that we use every day of tunnels. Another example that we've used a lot is due to the interworking of IPv6 and IPv4. Last week, we talked about interworking. How can I speak to a server that runs only IPv6 when I am only IPv4 or vice versa? We've seen that one way to solve this is to have, in fact, intermediate servers that will work at the application layer, that will translate everything I'm saying, or HTTP proxy servers. We've seen HTTP tunnels that will receive all the TCP segments and re-forward them by changing the protocol from IPv6 to IPv4. That's the interworking problem. In the nightmare of the combination of IPv6 and IPv4, nightmare for users, but good business and good opportunity for people like you, perhaps, and us, because this is a networking problem that requires a lot of networking expertise. We separate interworking from like-to-like access. Interworking is what we saw last time. Like-to-like is a problem that we had, for example, in the lab, when we have here at EPFL, the Wi-Fi of EPFL doesn't support IPv6. And we have a lab to do where my machine supports IPv6, and the server that we ask you to connect to also supports IPv6. So it's like-to-like in a sense. It's IPv6 that want to speak to IPv6, but the things in the middle are not all IPv6. That's exactly the problem. 6 to 6 over 4. That's a problem we have in the lab when we do it over Wi-Fi of EPFL. There are also similar problems, 4 to 4 over 6. This is, for example, the problem you have on cellular networks when you have an Android phone that has Android applications that use only IPv4, and your cellular operator gives you only an IPv6 address. I say Android because Apple applications must all support IPv6. So if you have an iOS application, it must natively run over IPv6, but Android not. So that's another problem. That's the 424 over IPv6. Yeah. There's an obvious simple way, which consists in making a tunnel. The name that often comes with that is the tunnel broker. Assume here you have your IPv6 domain, which is, for example, your PC with a virtual box and all the like, that is connected to the EPFL with IPv4 only and wants to talk to some part of the network of the world, which is IPv6. Let's call it the IPv6 internet. You want to speak to the IPv6 world here. Then what you can do is exactly the same thing that we saw a minute ago for virtual private network. Here, you can establish a tunnel over IPv4 to carry IPv6 packet. It's called a tunnel here. And here we will not use UDP. We will simply put all the IP packets, IPv6 packet, into IPv4 packet here. Of course, we need to configure our machine with the endpoint of the tunnel. And this configuration goes via what is called a tunnel broker. For example, For example, there are companies like Hurricane Electric that does it for free for you. So if you have IPv4 only somewhere and you want to run over IPv6, then you can configure a tunnel from your PC, whatever your PC is. You will need to configure things like you will need to know. So this would be Hurricane Electric that puts to the disposal of the world routers that agree to be endpoints of tunnels. They are called tunnel brokers. You will need to configure into your IPv6 configuration what is the IPv4 address of the endpoint. This IPv4 address is your IPv4 address, doesn't need to be configured, but this one you will need to configure it. And also what is the IPv6 address of the endpoint of the tunnel here. And also what is the IPv6 prefix that Hurricane Electric gives to you. So once you have that, so the Hurricane Electric or the IPv6 ISP must give you an IP prefix, must give you also the IP addresses of the endpoints. And once you have statically configured all this, it is as if you had a long physical wire directly here, and you're connected to IPv6. Of course, if you do this to go for lab 3, to go to our IPv6 server, you will first go to Hurricane Electric over IPv6, which will then go via the IPv6 world. Perhaps this is in the US, perhaps not, I don't know. And it will go via switch and etc. Will go back to the server of EPFL. And this will work if this is all publicly available here. So the path might not be optimal, but this will work here. And to the rest of the world, so to our lab 3 server, your PC here appears to be an IPv6 host with an IPv6 address that has been given to you by Hurricane Electric. So you appear to be on the Hurricane Electric network. In fact, that's the motivation of some providers to do that, because they give a service to a large customer base who hopefully sometime will become a paying customer here. Okay, let's assume we do this and we send back a packet to the IPv4 only, to the machine that is running IPv6 but connected to IPv6. So when our lab 3 server sends a packet back to you and we do a Wireshark at this point 1, 1 is perhaps between the IPv6 network of switch and the IPv6 network of Hurricane Electric. What do we see at point 1 among all the 4 possibilities that are given here? Close the poll in a few seconds. Closing. The majority says D, which is the correct answer. I mean, for this IPv6 world, we see this guy as belonging to the domain of this guy and being an IPv6 customer. So we send an IPv6 packet, and the destination is this IPv6 address here, which is the IPv6 address given to this customer. So no, this one. So the IPv6 address is the final destination address of this one here. Because the packet will be carried here by B because Hurricane Electric has configured its routing table by saying the prefix allocated to this, which is this entire prefix, goes via this logical interface, and it will reach router A. Now, router A is an IPv6 router, will have a table, or its on link will send the packet. So the answer is D. Correct. We've seen last week that MTU is sometimes a problem. How about the MTU here? What is the value of the path MTU between those two endpoints, between Homer and Lisa? Assume all links are Ethernet. All the physical links everywhere in this world are Ethernet with an MTU of 1500 bytes. I close in a few seconds. Closing. And the majority says C, but the correct answer is B, at least if we don't use Mpls. If there's Mpls, that might reduce the MTU here. But here, what will happen is that the packet is encapsulated, the IPv6 packet is encapsulated in an IPv4 packet. So if the IPv4 header is standard, it will have 20 bytes. So we remove 20 bytes from the payload, which is not available. So the path MTU in this case will be this value. So that explains why that's a value that we often find. If you find this value, that means there's encapsulation in IPv4. And remember, of course, if we have, if the tunnel is encrypted, for example, with all the bells and whistles we discussed a few minutes ago, that will further reduce the value here. So this is why path MTU discovery should be done, or you use the safe MTU values of IPv6. So this is how things work. In practice, there are zillions of variants of that. In particular, what is done today is 6RD. If you are at home over an ADSL modem today, you in Switzerland, you have IPv6. You will be given an IPv6 address. And this is done over an IPv4 infrastructure. So the operators are lazy. They have an IPv4 infrastructure that they've run and debugged for decades, so they keep it. And instead, what they do is exactly the same. They give you an IPv6 address by giving you a tunnel to their IPv6 world, which is small because there's not much native IPv6. But you will have an IPv6 address from home in most cases, which is exactly like all the things we said before, with one variant. 6RD and 624 are quasi the same. The tunnels are done automatically. How can we do a tunnel automatically? I mean, at home, I've never configured my ADSL modem with a tunnel endpoint. I don't need to do that, and I have IPv6, but I know that my provider access is over IPv4. How is that possible? Well, it's possible by doing the following tricks here. So we need to do a number of things that are done here. So the first thing is that so here what I'm explaining is 624. Those are two variants of the same scheme with this RFC that is called 624. We reserve a part of the IPv6 world to carry IPv4 address. So 2002 I read it as 2002, but those are hexadecimal digits. It's not the number 2002, but that's what people do. So the prefix 2002 followed by anything, followed by 32 bits that come from an IPv4 address that is reserved for what is called a 624 address. So for any IPv4 address, I add 2002 in front of it, and I have an IPv6 prefix. That's reserved for 624. So no one else, if you see a number 2002, you know it's a 624 address. And you know that the following 32 bits are a valid IPv4 address. So that's the first thing. So how is that used? Well, when I have this IPv4 address, 9.8.7.6, with this system, I know that I automatically have an IPv6 address that I can use, which is this one, 2002, and then I put into the syntax of IPv6 my IPv4 address here. And then I have not just one address, but an entire prefix. So I can have at home an entire IPv6 subnet, IPv6 network with multiple subnets that I can use. And though if my provider supports IPv624, I will have a valid IPv6 address here. Then how does it work? Of course, I'm connected only to IPv4. Then the other part to make that, so that will solve the problem when someone speaks to me. For example, I connect to a server and I receive the reply back. This is the address that I have. So the IPv6 world knows that this prefix 2002 means IPv4. So all routers in the IPv6 world, they have a route to the prefix 2002, which must be a router that is a tunnel endpoint that is both an IPv6 and IPv4 and agrees to be a tunnel endpoint. So in this IPv6 world, the packets to me will reach which is called a 624 relay router. That's a router that makes the interface between IPv6 and IPv4. Then this router will receive a packet with destination address, this one here. Now it knows that's an 624. Therefore, I can extract the IPv4 address from this IPv6 address. So I will create an IPv4 packet with destination address 9.8.7.6. I will put the IPv6 packet into it, and I will put it into the IPv4 internet. And if the routing is not broken in IPv4 internet, it will reach router A. And router A, now it knows it's an IPv6 in IPv4 packet. It will decapsulate and send it. So that solves the problem from Lisa to Homer, simply by having reserved a portion of the IPv6 world to carry IPv6 addresses. We've seen this trick already in another context. We've seen IPv6 we have seen mapped addresses from IPv4 to IPv6 that are used by dual stack servers that run both IPv6 and IPv4 when they receive an IPv4 packet and they want to treat it as in their IPv6 sockets. So there's a different way of embedding, and then it's with lots of zeros. Different ways of embedding IPv4 and IPv6. That's one of the two ways we've seen so far. That doesn't solve the problem in the reverse direction. In the reverse direction, how does an IPv6 packet that is created by Homer here, or by us in lab 3, and that needs to go to this destination? Well, for this, we need to reserve something else, which is part of the IPv4 address world that is reserved to mean IPv6. But here in IPv6, it was an entire prefix, 2002. Here is just one address. In fact, it's a /24. So 192.88.99/24 means this is the IPv4 addresses that those relay routers have. And that's a well-known and pre-configured address here. So my router here, when it has an IP packet to send on this 624 interface, it will do the following: create an IPv4 packet with destination address, this one, exactly this one, put the IPv6 packet into it. Now, this IPv4 address is not the address of a single router. There are many, many routers that respond to the same address. So this router B on this interface, it has in fact a normal IPv4 address, which is the IPv4 address that it uses coming from the domain where it is. plus this one. So it is configured with two addresses on the same physical interface. And many routers in the world have configured with the same. This is what we call an anycast use of a unicast address. We've already seen this in other contexts. This works, of course, as long as we don't run a web server with destination address this, because that might cause problems. But it works as long as we inject into the IPv4 routing this address. This will be injected by many routers, and the routing decisions, for example, if we use shortest path routing, we will go to the nearest of those routers here. So all this together create what we call automatic tunnels. We don't need to configure them. We don't need to configure because these two blocks, 2002 and this red block here, are well known. And if you decide to enable 624 on your router, this will automatically do tunnels to these two blocks of addresses here. 624 is not very much deployed today. It was deployed until some years ago, and it's replaced by 6RD, which is exactly the same thing, except the blocks are not well known. In fact, there was a drawback with this, is that 2002 is the same for everyone. But Sunrise does not agree to run a 624 relay router for the Swisscom customers. If we use shortest path routing or whatever routing is, we don't control to which relay router the traffic is going, which operators don't like. If you are a customer of Sunrise and you receive your ADSL modem for Sunrise, they would like that your traffic goes to a relay router of Sunrise, because they don't want to send they want to have full control of their own traffic. So that's the only difference. 6RD is exactly the same, except those blocks that I mentioned, 2002 and 192.88.99.1, are blocks taken from the blocks IPv6 and IPv4 given to that owned by the operators. So they are hard to guess. Swisscom decides which part of their own prefix they give to it. So if you go home and you look at your if you go look at the configuration of the ADSL modem, one way to know whether this is used, but as far as I know, this is how you get IPv6 address access in Switzerland. You will still detect it because you will recognize something like this, right? If I I monitor the configuration of my machine A here, I look what is the IPv6 address and the IPv4, I will see that the IPv4 address appears in the beginning of the IPv6 address here. That's a symptom that we're using 6RD. In the lab, we use Teredo, not 6RD, which is very much the same. We'll not go into the details of Teredo. It's using similar things, except it works behind a NAT. Here, I was assuming that it's my ADSL modem that is doing that. So the software and the configuration of my ADSL modem is controlled by my operator. Now, assume I have an operator that gives me only IPv4, like EPFL. When we are over Wi-Fi, we receive only IPv4. Then we cannot do that. We have to do something else because our traffic is typically behind a NAT, and the NAT creates complications. Those complications are the things that are solved by Teredo, which is called Miredo in Linux, which is the one we use. It was deployed by Microsoft some years ago, and for many years it was the default way of accessing IPv6. Now Microsoft has removed that because of security reasons. The perimeter of attack is large if we use this here, and Microsoft prefers to use other solutions like HTTP tunnels to solve this interworking problem in a different way here. Teredo and Miredo use a different block of addresses. The block that is reserved for that is 2001.0. So if you see an address that has this, it means that it's a Teredo address here. We will not go into all those details. So that the tunnels essentially are, and the automatic tunnels are solving the like-to-like problem, and that is a pretty much solved issue today. So in practice, everyone who is providing you with a box that gives you IPv4 address is smart enough to give you a 6RD software that will give you also an IPv6 service. There still remains interworking problem or the converse problem. There are other solutions. There are other solutions which are given here in this case of 4 over IPv6, which is the converse problem. What we were discussing is how can I access IPv6 when a provider gives me IPv4. Here I have the legacy problem. Legacy means I have old stuff. I have IPv4 only, which is becoming increasingly less frequent, except in the Android world. And I want to go to an IPv4 service, for example, Skype. Some Skype servers run only IPv4. And my service that I receive from my operator is IPv6. There are multiple solutions to that, but the widely deployed solution today is called this. It's a NAT solution. We've seen the NAT. And then what is the NAT doing in our example, in our day-to-day operation? It is translating private IPv4 addresses into public IPv4 addresses here. Here we can use the same technology, the same idea. Here, the public addresses I have are IPv6, and then the private addresses I use are not IPv6 private addresses, but IPv4 addresses here. So we can do a NAT and translate the IPv4 address into an IPv6 address here. This solution is called 464 XLAT. XLAT means translation here. The difference with the solution that we've discussed before is that there is no encapsulation. With 6RD, we put an IPv6 packet inside an IPv4 packet. Here it's different. We change the header at an intermediate point, exactly like a NAT does. A NAT changes my address. The rest of the world doesn't see my true IP address, which is a private one. It sees something else that has been changed. So it's the same idea here. So if you use this solution on the customer side here, customer means on the side of you and me at home with this IPv4 address only here. We also need to reserve blocks of addresses. So we reserve one block of IPv6 addresses here for an IPv4 customer. So assume you're a provider and you want to give this solution here. You will give IPv4 addresses, IPv6 addresses, for example, here. This block here is given to you, even though you are on IPv4, but the intermediate box will receive that block here. But as we have seen in the previous case, we always need to have two blocks to make the full connectivity. We need also to reserve another block of IPv6 addresses for the rest of the IPv4 internet, which is here, this block. So this block, I show it attached to this here. That means that if anybody has to send a packet to an IPv4 host that is on the global IPv4 internet, it must first send it to this, it will find a way to send it to this block of addresses here. And if you look at this block of addresses, it's a block /96. Why 96? Well, because 96 plus 32 bits gives exactly a full IPv6 address. So that's a prefix that you can add, and in the remaining part here, you will put an IPv4 address here. For example, when this guy that is on IPv4, for example, it's my smartphone running Android and has only an IPv4 application on Android, for example, and is connected over IPv6 here. So I have an IPv4 address, 10.1.2.3, and I communicate with someone else who has also an IPv4 address, 9.8.7.6. Then what this translation will do, it will transform this destination blue address into this one here. This is the block, the prefix of size 96 here. It will translate it, and this prefix is well known by this box here. It's given by the provider, very much like 6RD. So this mapping here is done by this CLAT, which is very much like a NAT, with one big difference, is that this translation now is completely automatic and dumb. There is nothing smart to do. You just put the add the address to the end. That's only 50% of the story. That explains how I can send a packet that has the correct IPv6 destination address that will reach this router here, that will translate this address and send it over the internet here. That doesn't solve the other part of the story because my private address here, 10.1.2.3, will need to be translated. And this can be translated by using the prefix here that is given to me here. So on this side here, everything is completely automatic and simple. Because the problem we had was to put IPv4 addresses into IPv6 addresses. That's always easy because an IPv6 address is big. So we reserve a block and we map everything. Where things get more complicated, it is in this 6 to 4 interface machine, this machine that interfaces IPv6 and IPv4. Now it has received a packet from me with an address that is, for example, this one, 2000 ABCD. That's the prefix, the IPv6 prefix given to me here. And my address here is in fact this green, which is a private thing here. Then what this machine will do, it will do a NAT function, but now a traditional NAT with all the hard work of the NAT. It will need to replace this address, which contains two parts. It contains my IPv6 prefix and my private IP address. It will translate it to, well, to what? Well, the only thing that it can translate to is an IPv4 address. For that, it will need to use an IPv4 address, which is given by the provider. You may remember that the 164 block is a block that is private addresses, but to be used by providers. So we need to reserve part of this IPv4 address space to represent all those IPv6 over all those customers that are IPv4 over IPv6 here. So this will be translated, but of course now, this is a usual NAT, we need the port number. Why do we need the port number? Well, if we wanted to avoid having the port numbers, we will need to make sure we have one-to-one mapping from every address from this block to all the possible addresses of all my customers here. Which first would be hard because I don't know how many addresses I have. I mean, you do at home what you want. You configure your 10.something network at home as you want, so you can have as many as you want. And second, there are probably much more here than there are there. I mean, this block is not so large here. So that's the same problem we had with NATs. In order to solve the problem, we re-engineer the port numbers. So that we will fiddle with the port numbers by mapping not just the address, but also the port here. So that's to translate this address into this one here. For the rest, for the destination address, the NAT has an easier job because the destination address was this one. And we know we simply get the IPv4 address directly from this without any difficulty here. So like a NAT here, it will be stateful for part of the mapping. So this solution, as you see, has a cost. The cost is to have a NAT. So this is deployed by a carrier like Swisscom. You need what is called a carrier-grade NAT. You need a big machine that will be able to do the NATing function for a large number of addresses here. Now, this seems a bit complicated. Let's see if the complication can be overwhelmed and see this question. Homer sends one packet to Lisa using this technology, and Lisa responds. And we observe the response at Lisa's interface here at 0.5. What do we expect to see? I close the poll in a second. Closing. And the correct answer is B. Of course, there is only an IPv4 packet, which has an IP destination address, which is in this block reserved here in the NAT. And of course, the machine will translate that and make sure things will work correctly. I'll skip the next quiz and conclude with this. Why did we see that in detail? Well, in fact, because this is solved, this is used, in fact, a lot as an alternative solution, not to the like-to-like access problem, giving 4-to-4 connectivity over IPv6, but also to do interworking. In fact, we can use the same elements here to allow this IPv6 only host to communicate with an IPv4 server here. So we use exactly the same elements here. The ISP needs to reserve blocks in exactly the same way. And the IPv6 host here can communicate with this machine here. Here I'm giving an example of a web infoscience. And this is the infoscience of the University Agostinho Neto in Luanda. I'm using this one not because it's Luanda, but we have the same problem at TPFL. Infoscience at TPFL works only on IPv4. Then we can do the same trick here because the 9.8.7.6 address here, we can map it to an IPv4 address, which is a IPv6 address. If we agree to reserve this block, which this provider will do. So the network provider, the ISP, needs to collaborate. It will reserve one block of IPv6 addresses for the IPv4 internet, this block here, and then any IPv4 address can be mapped into that. So it is now possible for this guy to communicate with this and send IPv6 packets to this host here, because the machine here will do exactly the same trick. The IPv6 destination address will be this one, so it will be mapped to this IPv4, and the IPv6 source address of Homer will be mapped to an IPv4 source address, which is in this block here. And we will do the NAT with port translation, exactly like we saw before. So it will be possible for Homer to talk to this machine. Perhaps with one little caveat. If I run IPv6 in lab 3, we've seen that we go to, how do we know that the server is IPv4? We go to DNS and we get a v4 or v6 address. But that's not a good answer here, because my machine is on IPv6 only. If I go to DNS and I see I have an IPv4 only address, I cannot go to InfoScience of Luanda, because I have, the only thing I have is an IPv6 access. I can communicate only IPv6. So what's the solution? Well, we need the collaboration of the DNS here. We will put into DNS a version of DNS that's called DNS 624. We will put in DNS an address, exactly this mapped address, that corresponds to an IPv6 address of this. So this is done by the provider that provides this transition mechanism. So for you, your machine is still configured as being purely IPv4, but your provider will cheat and will write in the DNS server an IPv6 address that corresponds to the block that the provider has reserved for customers like you, and with an IPv6 address that you don't even know that you have. So there is no, in this world here, there is no IPv6. So you don't even know that you have an IPv6 address, other than if you go and query the DNS. Well, this is what is deployed today for one of the other mechanisms. There is application layer gateway. This other one is the one that provides the ability for an IPv6 only host to connect to an IPv4 server. Well, we've seen a number of mechanisms. There are more. The bad news is there are even more, but I've seen them with you, the mechanisms that are the most widespread, at least today, might change in the future. And this is, I believe, almost the end of this course. I think we have Lisa, who would like to say Merry Christmas to all of you. I hope you've enjoyed this course, and I wish you a good and hopefully restful end of year. Thank you very much.